In the first lecture on the instrumentation amplifiers, we looked at how you analyze them and the improvements in them. In the last lecture, we looked at how you can improve common mode rejection ratio and how to analyze common mode rejection ratio by improving the matching resistors. We also looked at how you can actually separate any errors from the sensor by buffering it via two buffer amplifiers connected to a classical differential amplifier. In this lecture, we're going to look at how we can improve the performance of an instrumentation amplifier by modifying the design of the input difference amplifier to give us additional gain. If we place some resistors around the input amplifier such as this, then we actually can increase the gain of the overall instrumentation amplifier. And here we've called the resistors RA and RB, and they're arranged symmetrically around the buffer amplifier at the start, at the beginning of the input of the block. So let's look at why we would do this, and let's do some analysis on the benefit of using the buffer amplifier in this fashion. So by increasing the gain of by applying the resistors around the buffer amplifiers, we can actually configure a circuit that has a large differential gain, but remains to have a low common mode gain, in fact only ×1, and this is beneficial for our instrumentation amplifier performance. So doing some analysis around this circuit, let's, if we have an input signal at in plus, which is up here, then because we have a perfect op amp here, we have in plus superimposed here, and similarly on the negative side we have in minus applied here, so we have in minus applied here. Let's start doing the analysis of the differential gain of this buffer amplifier and see how it helps the performance of our instrumentation amplifier. So the first thing we do is we are going to divide this RB into two. So we've got RB2 upon 2 up here and RB upon 2 down here. No change to the circuit, we've just simply split the resistor into two halves, and this will help us do our analysis. If we let the input signal at input minus equal the negative of the signal at input plus, in other words the signals are completely out of phase and symmetric with each other, then we land up with this here. So at the top we have an in plus going into the top amplifier, and because it's the perfect op amp we have an in plus appearing at this node here. At the bottom amplifier we have an in minus down here, which superimposes the same voltage up here. Because this node here is exactly the same but opposite to this node here, then the midpoint of RB remains at 0, because although there's current flowing through RB upon 2 here, the same current flows through this resistor, therefore any voltage appearing across RB upon 2 up here must be equal and opposite to the voltage appearing here. We can now apply simple non-inverting amplifier theory here, so that the output at this node here is the non-inverting gain defined by this ratio here times the voltage appearing here, because this node is at 0, and similarly the voltage down here is equal and opposite to the voltage here. If we calculate out what the difference voltage is appearing between output plus and output minus, then and divide it by the difference input voltage at input plus and input minus, we land up with a differential gain equation for our input buffer set of 2RA plus RB divided by RB. And this is our differential gain. Now let's do the same analysis but look at the common mode gain of this circuit. So in this scenario, we let the input plus equal the input minus. In other words, they are both equal and in phase. So if input plus increases, then the signal at this point increases the same. It's the same input. Because they're both perfect amplifiers, this node here is the same voltage as this node here, Because they're at the same voltage, it means the current flowing through RB is 0, which means that the current flowing through both of the RAs must be 0. The output signal at output plus must equal the input signal at input plus, and the output signal at output minus must also equal the same voltage as well. There is no differential output voltage appearing between here and here. If we look at the common mode gain, which is the output plus the output minus, and compare it with the input common mode gain in a signal, we land up with a common mode gain here of times 1. When we apply the calculations across the whole of an instrumentation amplifier, we find that our input buffer stage has got a differential gain defined by the resistor values, but has a fixed common mode gain of 1. And from previous analysis, our differential gain of our difference amplifier is times 1, because the resistor values are all the same, and the common mode gain is equal to the delta divided by R1, precisely as we discovered before. So combining these two lots of equations, we can now say that the differential gain through an instrumentation amplifier is defined by this here, which is defined by the input resistors, and the common mode gain is defined by the mismatch of the difference of the resistors around the difference amplifier. Calculating out our common mode rejection ratio, which we know from definition and previously is the differential gain divided by common mode gain, we now have a common mode rejection ratio here, which is much higher because of the differential gain of the input buffer amplifier, and the overall performance of the instrumentation amplifier is equal to the differential gain divided by the fractional error in the resistors. So let's plug some numbers into that and see what that really means. If we have a differential gain of 1, in other words, the buffers and the amplifiers are connected as buffers, and we have 0.5% resistors, so we have a delta of 0.01, which is 2 times the tolerance, our common mode rejection ratio is of 40 dB, in other words 1 in 100. But if we were to increase our differential gain to 100 and keep the same value of resistors, our common mode rejection ratio increases 100 times. So instead of 1 in 100, it rises to 1 part in 10,000 as an error. If we go further and keep the same differential gain, but increase the matching of resistors from 0.1% resistors to 0.5% resistors to 0.1% resistor, we now have a common mode rejection ratio of 94 dB. So the secret of designing very good instrumentation amplifiers is to use the biggest gain possible that you can put in the first stage of the instrumentation amplifier, and then select the precision resistors that you require as necessary for the difference amplifier. So let's summarize what we discovered about instrumentation amplifiers now. Wherever we are trying to amplify signals where common ground noise or ground signals is a problem, the instrumentation amplifier is a solution to that, because the instrumentation amplifier provides a differential amplifier gain and rejects the common mode signal, which is appearing on ground. The classic difference amplifier has problems because it is sensitive to source impedance, and also it's very difficult to get high quality matching resistors. But using the instrumentation amplifier, by using 2 additional amplifiers at the input, we land up with very high input impedance, and we can increase the common mode rejection ratio by the differential gain of the input stage. Now, it's important to remember that common mode rejection ratio of a classic instrumentation amplifier and the gain are still linked. So you must use as much gain as possible in the input stage, but this may be limited to clipping or overdrive from the application circuit you're using. But the positive benefit is you can pay for resistors that are just good enough in the output stage so you can save money in the resistor matching components. I hope you now see and understand how instrumentation amplifiers can help being applied for very sensitive signals, for thermocouples or things like bridge amplifiers. In the next lecture, we'll look at some of the applications of these circuits and where you can apply this in real-world situations to amplify small signals and pass to perhaps digital processing units. Thank you very much.